Hey guys, welcome to the Curiosity Channel. It's the 21st century and computers are everywhere. Far from its humble beginnings as a room-sized calculator, the computer has become an integral part of our society. The average smartphone has more computing power than the machine they used to put the man on the moon. But despite the growing influence and accessibility of computers, our understanding of them has flagged. I mean, how does a computer work? Okay, so before we get started, I want to give a shout out to my friend John Remmert, who suggested this video idea. Computers are now. In fact, you are currently watching this video on a computer. Whether it's a standard desktop or laptop computer, or a mobile phone, or even a television, computers are everywhere. But despite the ubiquity of computers, their inner workings can still seem as mysterious to us today as they were when they were first invented. Really, on the inside, computers are just a collection of simple constructs put together in an ingenious combination to have amazing power. I'll go ahead and give you a flyover in this video, but as a caveat, be forewarned. This is less like giving you a tour of my hometown and more like pointing things out from a helicopter up above. So if you enjoyed this video and you're thirsty for more details, let me know in the comments. I might be able to put together a more lengthy series on how computers work. So to begin our flyover, the way a computer works is by taking in information, holding on to it, changing it, and sending it back out. These four stages have special names in the world of computer science. They're input, storage, processing, and output. Everything hinges on these four phases, so let's see how they work. Input is pretty easy. This is the starting information that the computer uses to do its work. Common input devices include a keyboard, a mouse, a touch screen, or even a camera or a microphone. Anything that gets information or files into the computer falls into the input category. For now, let's jump over to the output category. This is also fairly intuitive. Most personal computers' output devices would consist of a screen and speakers on the side, but really anything that the computer can send data to would be an output device, such as a door lock, a light, a robotic arm. Output devices. Where things get really interesting is the middle two phases, storage and processing. The modern computer we're all familiar with works off of electrical charges and currents. This allows us to designate a wire that has a charge as a 1 and a wire that doesn't have a charge as a 0. This means we can complete any calculations we need to as long as we work within a binary framework. Now, as an aside, binary is a special form of mathematics that works off of a base 2 rather than a base 10. Instead of having 10 different numbers or symbols that we can run through before we have to bump up a place, binary just has 2, zeros and ones. This takes up a little bit more space horizontally, but allows us to work with much larger numbers and much fewer distinctions. This concept is the basis of computer mathematics. Since each of these wires stores a 1 or a 0, this 1 or 0 is called a bit in computer science, we can chain these wires together with special connectors to perform manipulations of the signal. Of these connectors, or logic gates as they're known more formally, the simplest simply takes an input from a wire and flips it. If the wire coming in has a charge, then the wire coming out won't. If the wire coming in doesn't have a charge, then the wire coming out will. Since this gate does not give us the same value we started with, we call it NOT. Some gates are a little more complex and can work with two signals. For example, one logic gate takes an input from two different wires. If both wires have a charge, that is, a value of 1, then the connector sends a signal out the other side. If either of the inputs or both of them lack a signal, that is, they both have a value of 0, then the connector does not send a charge. Since this connector requires both the first wire and the second to have a signal, this is referred to as AND. Another such connector is the OR connector. This one outputs a signal if either the first wire or the second has a charge, and only returns a 0 if neither wire has a charge. With these gates and a handful of others, we can create more complex procedures to calculate on a signal. By combining an exclusive OR gate and an AND gate, we can create a structure known as a half adder. The structure takes two wires coming in and outputs the sum of the two. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 1, 0. Notice that the last result is a little odd. Remember, we're in binary, so 1, 0 is actually equal to 2 in our familiar base 10. Since that last result needs 2 digits to express the 1 and the 0, our half adder has 2 output wires. We can link one of these output wires into the input of another half adder to continue adding larger numbers. It's just like carrying the leftover numbers when doing longhand addition. If we want to handle larger numbers, we just need to upgrade our half adder into a full adder. From there, we can chain more and more full adders together until we can express as large a number as we need. One common structure is an 8-digit number, which needs 8 wires side by side. These 8 wires allow us to work with numbers that require 8 places in binary, or up to 256. This 8-bit structure also has a special name and is known as a byte, with a Y, because computer scientists are obviously not nerds. Once we've assembled these numbers, we need somewhere to store them. Data storage comes in a variety of forms, but they all boil down to roughly 3 categories: magnetic, optical, and solid state. Each of these varieties has their own merits and flaws, so we use each one for different purposes. Magnetic storage is the cheapest method, but it is also the slowest. So hard disk drives, used for long-term storage, place the data onto magnetic disks inside the computer. Optical storage, such as CDs or DVDs, are more stable and harder to erase or corrupt, so these make good storage devices for data that travels between computers. The newest form of storage, solid state or flash storage, uses electronic data storage and creates persistent data. That is, data that remains in place even if the power to the system is cut. This is the type of technology we use in flash drives, SSD, and even RAM, the short-term memory or scratch paper that the computer uses for calculations. But how exactly does the computer perform these calculations? Well, through ingenious usage and organization of the logic gates and adders we talked about before, we can construct an arithmetic and logic unit, or ALU. This component does all of the computation on each number we need to effect, capable of addition, subtraction, incrementation, and more simply through a clever organization of logic gates. However, this ALU is useless without the main brain of the computer, the central processing unit, or CPU for short. This is the hub of all activity in the computer and runs programs and processes to read values, run calculations on them, and send them to the proper storage or output device. So if you sit down to work at your computer and type a few keystrokes into your keyboard, that information is sent down to the CPU, which decides what processes to run on the information, sends the instructions down to the ALU, which runs the calculations, and sends all of that back to the CPU, which, by the help of a GPU, if present, will process that information for output and send it on to the output devices. Phew, that was a lot. Well, I hope now you have a stronger understanding of how computers work on that architectural level. Again, if you were interested in this and you'd like to see a longer series about computers later on in the future, let me know in the comments section down below. For now, get out there, crunch some numbers, and stay curious, my friends. Hey guys, hope you liked this video. If you did, go ahead and hit the like button, let me know I'm doing something right. If you had any questions about this video or any suggestions for a later video, go ahead and drop them in the comments section down below. If you haven't yet subscribed to the Curiosity channel and you'd like to keep up with all of the latest, go ahead and hit that subscribe button. We'll keep you posted for a new video every Monday. Thanks again, and I'll see you next time.